This is the second half of section 5.1. We just got done doing this, or these formulas for mean, variance, standard deviation, all that stuff. And then we did one for, I don't know, for flipping two coins. So the probability, the mean, variance, standard deviation for flipping two coins down here. So if you flip over to the next page, we're going to kind of analyze this data a little bit after we solve for and find the mean, variance, standard deviation. What you're looking at here, you've seen this little strip of dotted line before, or a strip of arrows before. Your mu is going to be your mean or your average. And then what you're doing to find the significantly high values is you're adding two standard deviations or subtracting two standard deviations. Adding two, subtracting two, those tell you significantly high values or significantly low values. In a similar way, like I know that we've talked about before, like two standard deviations is 95%, right? 95% of your data, according to the empirical rules, should live within two standard deviations. So a value that's significantly high is like 0.05, is like beyond the 0.05 mark. Similar to that, if it's a significantly low value, it's 0.05. Now, those don't add up to be 100%, right? Because 0.05 plus 0.05, that's going to be 105%. But when you're dealing with significantly high values, you're typically not dealing with these over here. So you're looking at from this point and beyond, and that's only 100%. Or if you're dealing with significantly low values, you don't have any significantly high values, so you're only dealing with this point and beyond. So that's why if you're like looking at this, like that doesn't add up to be 100%, that's why, okay? So 0.05 is really that threshold that we usually have, and that tells us whether something's significant or not. So example 4. They want to identify significantly high and significantly low values. So we found that when tossing two coins, we did this on the page before, that the average number of heads is 1. So my mu, if I do that on a number line, my mu is 1, my average is 1, okay? And my standard deviation was 0.7. I think it was like 0.707 or something like that was what our standard deviation was. Anyway, use those results and the range rule of thumb to determine whether two heads is significantly high or not. So we have this point right here and this point right here. That's two standard deviations below, okay? We're looking at two heads, so we want to know, is two heads, here's one head, that's the average, is two heads a significantly high number if our standard deviation is 0.7? So this part right here, if we add one standard deviation, it would be 1.7, and if you add 0.7 again, that's 2.4. Okay, so two heads would live somewhere in here, and it is not inside that significantly high value. So no, having two heads when you're flipping two coins is not really that big of a deal. Okay, you don't go, wow, I just got two heads if you flip two coins. Not significantly high, right? It's not that big of a deal. All right, so, and that's why it's not more than two standard deviations above the mean. He lives right here, not important. Okay, significantly high numbers, I just said up here, was anything where the probability of that happens less than 5% of the time. A significantly low number is the same thing if the probability of that happening is less than 5% of the time. Okay, so same scenario here. This happens less than 5% of the time. This happens less than 5% of the time. That's really like, wow, I can't believe I got this type of thing to happen. Significant values, less than 5% of the time. Okay, so down here they're just going to have us analyze that data. It says identifying a significant result with probabilities in 252 heads, or is 252 heads in 460 coin tosses a significantly high number of heads. Okay, so 460 coins is what we're tossing. If we divide that by 2, it's 230. We should expect that approximately somewhere close to 230 heads will show up, okay? Because there's a 50-50 chance of getting a head and tails. So 50% of them should come up heads. Is it going to be exactly 50%? No. But this bell curve says that the majority, or the highest tower here, is exactly at 230. Most of the cases when I flip 460 coins are going to land with 230 heads up. Okay, and then it kind of tapers off from there. Okay, I might get, like, every so often I might get some that are way out here that I have way a lot of heads. Okay, so I don't know why it says 249 here. I don't know, this should be 252. I'm looking at those numbers right now. Maybe I typed something in wrong. Anyway, it goes ahead and gives me these numbers. So it says that the probability of getting 252 or more heads, or more, because we're looking at this entire interval here, 252 or more, this chance of happening is 0.0224. Okay, so again, if we look at that, like, significantly high values, this is, if we relate this back to a bell curve, it's doing this. Ooh, I can't make my bell curve very tall. Okay, so like this little tapered edge over here and this little tapered edge over here. Those little guys can't be any more than 0.05, otherwise it's not significant. So 0.02, 0.0224 is less than 0.05. So we conclude that it is significant. Okay, it's happening way small amounts of time. Okay, there's not very often do I get 252 heads if I'm flipping 460 coins. Okay, not very often does that happen, so I'm going to say that that's significant. If I get that many heads, it's kind of a big deal. All right, going to the back side. This is part 2. Which is talking about expected value. Okay, expected value is the mean. You can expect the average, right? You expect the average thing to happen. So if I'm flipping 2 coins, on average I should get 1 heads. I would expect that 1 would be heads and 1 would be tails. Okay, it's not always going to be that way, but my expected value is calculating the mean, figuring out what that average is. Okay, so what we're doing here for expected value is we are, in example 6, placing bets here. So we have an A and a B, and we're trying to decide which one is the better bet. Okay, do we want to bet on the number 7 in roulette, or do we want to bet on the pass line in the dice game of craps? Okay, I have no idea what these games are, but they're going to explain that down below here. So we only have $5 to bet. Okay, we want to decide which bet that we're going to place on. Okay, which chance, which scenario gives me less of a chance of losing money, or if I'm going to lose money, losing the least amount of money. All right, so roulette and craps is what we're playing. All right, the first one explains to me, and they have a table set up for us already here, and I left those values in there so we didn't have to fill them in at all. If you bet $5 on a 7 in roulette, the probability of losing $5 is 37 out of 38. You only win 1 out of 38 times. Okay, this is my winning. This is my losing. Okay, so if we look at that down here on the table, they have it separated out into lose and win. Okay, if we lose, we're going to lose $5. If we win, we are going to win basically $180, right? We're going to win $180, which means we actually win $175 because we bet $5 to start with. So you're going to win $175. So that is your X value, okay? Again, we're going to calculate the mean here in just a second, and I'll give you that formula again. So 37 out of 38 times we're going to get lose $5. 1 out of 38 times we're going to gain $175, okay? So when we're calculating the mean, we're doing the expected value, okay? And the mean is the sum. This is mu. Mu is the expected value. Is the sum of all the x's times the probability that that's going to happen. Okay, so I'm taking these times those. Okay, so if I take -5 times 37 over 38, I get this really, really long decimal. They left it as a really long decimal. 175 times 1 over 38, I get this really long decimal, okay? And then when I add those two together, what I have come out is negative 0.26. So basically what that means is that I can expect to lose 26 cents on average each time I play. I can expect to lose on average 26 cents every time I play. Okay. Now, eventually I'm going to get to the point where I win. Okay. But if I keep averaging it about over time and I keep playing and playing and playing and playing, it's going to average out to me losing 26 cents each time. Okay. Even if I win every once in a while. All right. Now, if I bet $5 on a dice game, $5 here, there is a 251 out of 495 is the probability that I'm going to gain $5. Okay. So the odds are kind of 50-50. A little bit more than 50-50 actually. Then I'm going to gain $5. Okay. There's a 244 over 495 that I'm going to just lose it, right? So I have, again, lose, win. I'm going to either lose $5, and that happens 251 out of 495 times, or I'm going to win $5, 244 over 495, all right? And again, I calculate that mu, which is my expected value, is this x times the probability, and I add them both together. So I take these x's times this probability, and I get this, okay? This x times the probability, and I get that, okay? And if I add those up both together, I get negative 0.7, which means that I can expect to lose 7 cents each time I bet. And I'm going to put on average. Okay. I expect to lose 7 cents each time on average when I bet. So now you have to decide which one do you want to do. Okay. If I keep playing and keep playing and keep playing, on average, what's going to happen is I'm going to lose 26 cents. On average, I'm going to lose 7 cents here. So even though the payout is better up here, right? Every once in a while I'm going to win big, and I'm going to win $175 versus winning $5 down here each time. But this one, if I keep playing over and over and over again, I'm only going to lose about 7 cents each time versus losing 26 cents each time. So this one actually has the better payout, the better average. Okay, so what I went ahead and did is I left for you 3 more homework problems. And the first one, number 1, kind of goes back to what we did yesterday, where you're just finding the average, the mean, or the variance, and the standard deviation. So you have those formulas. Go look up those formulas. The average formula is right here. The other one for variance, standard deviation are here. So look at those formulas. Look again how we did this table down here, and you should be able to calculate those again. Okay. Number 2, A, B, C, D. All have to do with this information right here. There's nothing else that you need to calculate but adding these probabilities together and answering these questions, okay? You don't have to calculate mean, variance, standard deviation, none of that. Just answer the questions based off of that table. And then number 3 is going to be very similar, finding your expected value to this last scenario that we did, where you're like betting. I think we're talking about like life insurance or something there, okay? So this problem number 3, kind of base it off of this one, and then you should be good to go. You should be able to answer A, B, C there. So do those 3 questions, and that's it.